Hello everyone. This talk is about some concepts that can be applied in Scala and Java. Most of the concepts work in both languages. A few work only in Scala. And then there's going to be a demo session at the end. If you feel like tweeting about this, see, I did remember. There's your hashtag for this particular talk that I give. It's Akka Future. No S at the end. AKKA Future. The talk I'm giving is excerpts from a book I've recently published. And if you want to remember, where's that URL again? The cards that are on the food table shows you the URL if you wanted to get a copy. Agenda for tonight, I'm going to give you a little review of concurrency. Most of this stuff I would expect the audience would know, so I'm not going to bore you to tears with things that, oh, I knew this 10 years ago. Then I'm going to bring you up to date with some things I'm pretty sure you don't know. And I'm going to either define or redefine some terms, talk about functional programming a little bit, and explain why I'm talking about it at that time, and then how to tune things for concurrency, and then my demo. And as I said, this is all based on material in this book. So about myself, first of all, I'm a consultant. I'm a principal at Micronautics Research. We're a design build firm. We do neat stuff for people who need programs written. I'm an architect. I do some mentoring, some training, hands-on guy. Sometimes a company needs an interim VP engineering and they might give me a call. I work as an expert witness in U.S. federal court if somebody's suing somebody. This is my third book. I have a particular interest in artificial personality. I put that out in case there's somebody else who would like to talk about that at some point. And that's basically the technology that I'm speaking about tonight underlies the software I've written in that regard. I coordinate 2 user groups in the Bay Area Scala enthusiasts, and I co-coordinate, co-lead Scala for Startups in San Francisco. I'd like to learn a little bit about you now. Who here is a full-time programmer? Who here is not a programmer? Who here is a student intern type? Who here does not know anything about Scala, or very little? Okay, of those with your hands up, who would like to know something? Okay. And intermediate, if you are programming Scala, those of you who know what an implicit is and how to use it, put your hands up. 3, okay. And there's no sense asking if there's any experts here, because there'll be a number less than 3. And so I would assume that a number less than 3 is working currently now on Scala projects. 2, 3, okay. Who here is working on Windows? Doesn't have to be exclusive. Is one of the operating systems you're working with Windows? Who here is working with Linux? A lot of you. Who here is working on Macintosh? Not so many. This crowd's different from the last crowd. Who's working on something else an operating system I didn't mention? 3, okay, cool. All right, so this slide is the basis, the rationale for the whole talk. And so I'm going to spend a few minutes going over this slide. Once upon a time, prior to 2003, we software people expected that every year we'd have a higher clock rate. And probably only had 1 core on the machine on our desk. Maybe the server had a few more. But we looked forward to the higher clock rate next year. And that's how we were going to push more bits. And that changed in 2003. This is a semi-log scale. So the vertical axis compressed. And if it was a linear scale, then you would see that the number of transistors per year continues to kick up at a great rate. So what's happened is that we've plateaued. This red line is the clock rate, and it's not going any faster. And so long as we're using silicon, as opposed to, say, germanium or sapphire or diamond as a substrate, it's not going to go any faster. We've hit the physical limits. And so those extra transistors are going into more CPUs and bigger caches and things like that. And right now, this laptop has 8 cores. It's an Intel i7. I expect in 10 years my laptop, if I have a laptop, will have 50, 100, 200 cores. Lots more cores are coming. So if you're writing programs that aren't inherently taking advantage of those extra cores, you're stuck in 2003 and you're not going anywhere. You're frozen in time. So this whole talk is about how do you use all those extra cores. Here's the review part that should be completely boring, so I'll make it short, because you all should know what threads are. And just to remind you, threads are expensive. Thread is what you need to have many threads so that you can do many things at once. A thread just provides a context for a unit of execution. And so the more threads that are active, the more work you can do. So if you can only have one thread happening at a core at any instant in time, obviously having more cores means that you have the potential for more active threads. As you know, threads can be blocked, waiting for I/O or so. They're not doing anything useful. And if that's locked to a CPU, it's not doing any work for you either. So the trick in concurrency, or one of the things that you need to worry about, is how do we keep all these threads gainfully employed? There is a problem, though, and that is that threads can interact, and the caches can give you problems. So I'm going to show you a frightening example shortly. Because if you're not frightened, you're not going to buy, right? Isn't fear the basis of all sales? I make no money no matter what you do here. It's just trying to be funny. It failed, I guess. So multi-threading. We have in this little diagram a main program. It spawns two threads. One of those threads spawns another thread. And then the main program stops. And yet the other threads keep going. And they only can do that because the thread pool, the executor that is basically, there's an executor that says, you want a thread? Here it is. I've got a pool of them. You want another one? Here's another one. That thing keeps working after the main line stops. And you can have a thread pool that doesn't work that way. It uses daemon threads. And so if your main line stops, everything stops. All the work stops. It's over. A lot of programs, that's undesirable. So in this little main line, which is typical of the software I'm going to be speaking of most of the evening, the main line runs to the end, and the pool keeps its threads going. They call back to their calling point, and then they exchange data somehow. Maybe you had a map reduce, you consolidate information, and something finally happens, and then everything shuts down. So I mentioned callbacks, right? And Java provides you some standard thread pools. You can customize these, you can make your own. None of this is news, except if you slept through JDK 7. So there's, cached and fixed and scheduled. Who would like me to talk more about these different types? I'm going to skip by them unless you'd like more detail. 2 people, 3 people, all more people. Okay, so I'll go into a little more depth then. I didn't want to bore you. So a caching pool is where you have n threads, where n is usually set to the number of processors initially allocated for a task. And if more threads are needed, they can be created and added to the pool and used in the program. But if threads are idle, they go back into the pool, and by default, the standard implementation is after 60 seconds, the threads one by one disappear. And so after a while, you will have no active threads and no threads in the thread pool. So a caching pool is nice if you want to have a very light footprint. But it is not good if you want high performance, because if later you need those threads, you have to create them again and add them to the pool and give them a task, and all that takes time. It's noticeable. So in that case, where you need to have everything hot, ready to go, a fixed thread pool is better. If you want to have something that happens on regular intervals, scheduled pools are good for that. If you want to have just one thread, perhaps pinned to a resource, and your thread pool is basically dedicated to serving that resource, a single thread pool is good for you. And then there's the single scheduled, where you have this one resource that happens periodically. So JDK 7 added, it was a JSR 166, if you must know. You're going to hear that again, so I'll say it again. JSR 166 gave you fork join, and it was a more complex algorithm. It's kind of like the caching idea, except it's a lot more sophisticated, has a little higher overhead. So if you have callables or tasks that are very, very small, this is not the algorithm for you. But if you have non-trivial amounts of work, and especially if they're recursive in nature or subdividable in nature, this is an excellent task. It balances its loads, it watches itself, it's self-aware. And so fork join is evolving, whereas these other thread pools are not. JSR 166Y was improved, and so the version that's currently in JDK 7 will be better in JDK 8. If you want to use this better algorithm, you have two choices. You can download JSR 166Y and link it in, it's a jar, and then you can call that a version. Or you can use the Akka version, which has got this new version already in it. And Doug Lee, who's done this work, continues to make this better. So it seems like every few weeks or months, he says, and now we made it even more interesting. I think there was one of those that came out last week. So you can take these, and I've done this, we take a thread pool and mess around with it and change its characteristics or change the scheduling. Not for the faint of heart, not because it's so hard, but this is something that you don't want to go wrong. And it's hard to test. These things are non-deterministic in nature. And so you can be brave and say, there, it's done, and find out a long time later, after something really bad happened, and there's this little tiny problem you didn't see. So I would suggest that you don't mess with these. You have another option, and we'll get to that. Basically, Akka is giving you the ability to take all of these, to use any of these and other variants of them, and in a config file, just specify the properties you want, and it'll put it together for you and say, here's your thread pool. That's really nice. And you can do it at deployment time, not a program. The programmer doesn't have to do this. So basically, the program you test is the program you deploy, and you can measure it. I'm getting ahead of myself. It's a great thing. So here's some definitions. You may not like these definitions. You may have different meanings. I'm putting them out so you know what I mean. These definitions I'm about to give you that you can see are more common in the functional programming world. So Clojure and Scala programmers would tend to agree with this more. If you are a C++ programmer, you may not agree with these, but that's too bad. This is my talk, and I'm using these words just so we understand each other. So, concurrency. I say, for the purpose of this discussion, and you can disagree if you want, but for the purpose of the discussion, we will agree that the word concurrency refers to a task that has state and communicates with other tasks, possibly via an exchange of state. Now, another definition, parallelizable tasks are tasks that are stateless, that do not interact, and they are also composable as a result. So concurrent tasks are not composable. What's composable? I'll get to that. Just remember that concurrency equals not composable, parallelizable, composable. And yet composable is useful sometimes. j.u.c, java.util.concurrent, is the basis for everything we do in the JVM that requires many things going on at once. See, I didn't use the word parallelizable or concurrent at that time. It's getting awkward. What word can I use? So when you've got many threads happening, j.u.c is your foundation. There is this, we're talking about futures, so that's why, so hopefully you came here. Futures are designed, they're kind of like a container that holds a callable, and that callable will return a result, and that result will be in the future. And just to refresh, because probably a lot of you may not be clear, an executor is kind of like a factory for a thread pool, and it also has the property of being able to manage the thread pool that it creates. Now I'm going to talk about executors, and you can say, what's that again? It's the thing that handles thread pools. And if you have an executor service, which was, it's an interface of a thread pool, let's say, you can shut down the thread pool by calling shutdown. Okay, so I'm almost finished reminding you what java.util.concurrent does. Apologies if you've heard this before and you'd like us to move on, but it's important to get this solid. Callables and runnables are payloads. Okay, so it's a unit of work that you want to do, or it's a thing that's going to perform something of value to you, and it needs a place to do its work. And so we'll call that a container, all right, in the sense that a future accepts a callable and assigns it, it's backed by a thread, and that's how it does its thing. So java.util.concurrent gives you everything on this slide. It gives you callables and runnables and threads and thread pools and executors and a bunch of things I'm not going to talk about, which you may be aware of: completion service, countdown latches, concurrent collections, cyclic barriers, phasers, semaphores, time units, and a primitive version of future which isn't good for a whole lot because it's not composable. What's this composable mean anyway? What's he babbling about? It's coming. So what I want to put forward here is to say that to use these primitives that java.util.concurrent is giving you is very difficult. It's not, now as an engineer, I think I'm smarter than you. Give me the library, I'll make it work, right? Okay, well, it's nice that you're so brave, it's nice that I'm so brave, but the non-determinism from concurrent threads is exacerbated by what's going on in the silicon below your program. You've got high-level language, Java or Scala or Clojure or whatever. You've got assembler language, and then you have level L3 cache, L2 cache, L1 cache, the register file, and main memory. And what's going on between the three caches, the register file, and your main memory? You have many copies of the same variable. It's possible for multiple processors to have different views of the same variable, even if it's marked volatile. What? Okay, so let's talk about this. This is my attempt to scare you, all right? If you're not terribly frightened, I won't feel bad. But I would like to motivate you to say, first of all, if you have an AMD processor or an Intel processor, the details will vary. The L1 cache, level 1 cache, is tightly bound to a processor. So the processor has a register file. There's not many of them. They're very, very fast. They're backed up by a level 1 cache, which has an image of some of the variables. They're pretty fast. Level 2 caches might be shared, depending on the architecture, I don't know if we're talking AMD or Intel, between pairs of CPUs. Level 3 caches are shared by all the CPUs on a die. And then you have main memory. Much, much slower. It takes hundreds of CPU clock cycles before the memory turns over once. And so when you fetch from main memory, everybody's waiting. So if your L3 cache is invalidated, there's not a whole lot going on in your CPU. So all processors are different, even from the same manufacturer. The size of these caches are different. How the invalidation happens is different. And so it's possible that you can get yourself in a situation where it works perfectly on your test system and it screws up horribly in production. And so now we come to cache line ping-pong. Now this comes from an article I read a few days ago, and it's a perfect segue for some other material I wanted to give you. The guy who wrote the program and wrote this article that I came across didn't know a lot about concurrency, so it's kind of amusing to see what happened. He said, oh, look, I've got some work I need to have done, and I can do it on one thread, and it takes so long. But if I do it on 2 threads, it should go twice as fast, because I can divide the work into 2 and give it to the pieces and combine the results together. And if I do it on 4 threads, it should go 4 times as fast. And I've got 8 cores on my machine, so I should be able to get it done 8 times as fast. And what he's doing is he had each thread, when it was finished its work, it would write a value into an array variable. So he's got, you see there's 8 slots in this array. So thread 1 would write into A0, thread 2 would write into A1, etc., etc. So he's basically said, okay, you get that slot, you get that slot. Here's what he found. Now, this is his graph, not mine. I would have done the opposite. He's showing speed increasing with the green line. This is as expected. So that's top speed. That's top speed. And on the lower left, that's 1 core. So what you've got is, as he adds more cores, he's expecting things to go faster and faster. But what he found was those other lines. As he added more and more cores, it went slower and slower. In fact, with 8 cores, it went at 1/10 the speed that he expected. And so as he added more cores, his program slowed down. Well, why is that? So it's a messy explanation. It's the MESI protocol is the reason. Remember the L3 cache on your processor. That cache can be in one of 4 states. It can be modified, which means that one of the CPUs has written something to it. It can be exclusive. We're ready to write. It can be shared. It's not dirty. No, it's in good shape. Or it's invalid, which is when things get messy, because you've got to wait hundreds of clock cycles to talk to main memory to pull. The big deal about this is that that L3 cache fills in chunks. And depending on your processor, that chunk size might be 64 bytes or 128 bytes, or we don't know because it's now the year 2015 and it's pulling at 1 megabyte. So when it becomes invalid, all of those variables have to be fetched again. And yes, they're fetched together, but if you had a computation pending or you wanted to write a value back, all your CPUs are stopped. You're starting to get a clue as to what was wrong here. So remember, each one of his threads was individually responsible for writing its answer back to main memory when it was done. But they're all running on different CPUs. And so when one CPU would write the answer, that would invalidate the rest of the cache. And so the next CPU wanted to write its answer about the same time. Well, that cache had to be reloaded so that he would write his value. But the first CPU's value was gone now, and so you have the ping-pong. You have 8 CPUs thrashing. His mistake was that he had the threads directly writing to shared memory. Now, it isn't that each variable was shared between different threads, but that in this block which was fetched, you had multiple accesses, multiple writes to the block. Most of the literature you're going to find talks about a variable being written to by 2 threads as being a problem. This isn't that case. These are separate variables. They happen to be next to each other in memory, and they're part of a block. And the whole block's gone, and you get the thrashing. Surprising? Tell me you knew this already. Who knew this already? Yeah, I mean, I didn't know this. So what can you do about that? Here's the java.util.concurrent solution. All these slides will be available. I've written this in Scala, but you can imagine what the Java would look like. I'm saying we've got the whole array is volatile, and I'm synchronizing access to it. And you say, oh, but synchronization is so slow. Well, it's not as slow as what we saw before, where everything slowed down to 1/10 of what it should have been. So this is actually a lot faster. But it's still not the right way of doing it. If you have multiple threads writing their answer to some spot, it's very hard to manage your concurrency. And yet this is the way things had been done before. Or if you're not a functional programmer, this is what you might think of. If you're using futures, you would not be doing this. So the other morals are, don't access external mutable state. Now, when I first wrote this, I said, don't access shared mutable state. But we're not even sharing, are we? It's just mutable state. The fact it's mutable and it's next to each other, and you don't know how far apart to spread it, because even if you put them 257 bytes away from each other, next year's model of the CPU will fetch an even bigger chunk for L3, and you're screwed again. Okay, so Prismatic, who's starting to make themselves known, have a really cool web service, has these guidelines that I thought were very apropos for this talk. Functional programming techniques will help you with multi-threading issues. The kinds of things that I just showed you that I hope you're feeling somewhat shocked and in disbelief. How could this be? Functional programming will actually help you with that. And so they're saying fine-grained, flexible abstractions. What? I'll show you some examples. Compose the abstractions. Use that compose word again. Composition is important. And then lightweight custom abstractions are much more efficient than large frameworks. And they cite Hadoop. I have nothing against Hadoop, except it is a big framework. It requires a lot of hardware, and it has a purpose. But if you think MapReduce automatically, bingo, Hadoop, wrong. I'm going to show you some MapReduce that will happen on your CPU here before we go. And it's very fast, very powerful. You may not need Hadoop for everything you're using it for. Okay, so now I'm going to explain composition in terms that you should already know. Who here has worked with Unix or Linux or Xenix or any of the Nixes? Great, that's what I expected. So you already know what I'm going to tell you. You have a data source. It's in a file. We can cat that, right? So we're going to list it. Then you can sort it. So what's happened is we've taken the original data source and we catted it, run it through sort. Now we have another data source. We haven't actually modified the first data source, and we've transformed it. And then we run it through unique. Another transformation, and we have yet another data source. These are temporary data sources, but we're still not messing with the original. And then we run tail on that, chop off the rest, and we have the end result that we wanted. This is functional programming. This is composition. Composition, all it is you tack a bunch of transformations together, and functional programming is just, you start with some data, you shove it through all those operators, you don't change the original, you don't change the intermediates, maybe you discard some of them, and you end up with what you needed. This scales, this is thread safe, and that's the essence of functional programming. There, you can go home and say you can do that now. And you've known it for years. So with Scala and with Akka, and because Akka works from Java, you can also do this in parallel. So first thing you have to do is you've got some data, you need to break it into chunks somehow. So you have a recursive algorithm or something that can be taken apart. Then you run it through some kind of transform. I called it map because map is kind of a generic do anything. You can almost do anything with a map. But feel free to write in your favorite transform there. They're all happening on different threads. At least they're on different stack frames. And then there's a reduce where you take all the intermediate results and you collect them together. It's the same thing. It's composition. It goes in a box, you get a temporary piece of data, goes in another box, another piece of data, boom, the result. So, armed with that knowledge, which you already knew, I'm going to tell you that there are, if you're a Scala programmer, 5 concurrency options. If you're a Java programmer, you've got 4. So j.u.c is common. Those primitives are available to you, and sometimes you need them. So if you weren't familiar with everything I showed you on that slide a ways back when it said, here's all the things you get with j.u.c, you should know them. Sometimes there's nothing like using that. If you're a Scala programmer, the next simplest thing you can do that runs on many cores is to use parallel collections. If you're working Java, this isn't an option for you, but it's fall down dead easy. It's very simple. I've got an article coming out next week on the 23rd in InfoQ magazine, and I'm going to be talking about Scala parallel collections and Akka Futures. So Akka Futures, and they're very similar in many ways to Twitter Futures, are the next step. They have many characteristics that are similar to Scala parallel collections. They're more flexible, so they require a little more understanding of what's going on. But what's nice about both Scala parallel collections and Akka Futures is that they're deterministic. You can reason about them. It's with not a lot of time, you can be pretty sure what's going on. Unlike Akka Actors, where you're building an operating system, essentially, it's not deterministic, it's not composable, and it's a much, much bigger piece of work. And then in between, you've got this thing called Dataflow. I actually should have gone through these slides here. So I realize I'm jumping ahead of myself. A few things I should have told you about Scala parallel collections. They block. So you've got your piece of data, you chunk it into smaller pieces, you throw it on the Scala parallel collection, and you wait. And when it's done, you take the answer. but they are composable, they're easy to work with. And they use fork join pool. So if you're running on JDK 6, which doesn't have fork join pool, Scala parallel collections actually have JSR 166 buried in the Scala library. So no worries. So the interplay between this Akka library, it's a library, it's a runtime library, that's all it is, and java.util.concurrent is, at the bottom, j.u.c is the enabling technology. Everything's built out of that. You've got futures that you can access from your application, just like you can java.util.concurrent. And you've got actors which can also interact with futures. The way this is drawn is not meant to say actors are more better. They're not necessarily better. There's a lot of hype about that. Oh, actors, they've been around 40 years. There is a place for actors. In fact, there's some things actors can do that nothing else can do. It can do distributed concurrency. You can have, with Akka actors, you can have many motherboards, all singing and dancing in harmony with a lot of complex interactions going on, and it's very fast. And I don't know as nice a way of technology that can do that. So the point of this is just to say, use the right tool for the job. Now you have 3 hammers. You've got a hammer, you've got a screwdriver, you've got a jackhammer, and you can look for nails and screws and, I don't know, posts to dig out of the floor. Underneath what makes this possible, on the right-hand side, the dark blue, we have java.util.concurrent stack. So you have executors. I'm not going to drag you through every box. I'm just going to arm wave. If you can't read it all, that's fine. You're not intended to. You've got executors, you've got thread pools, and those things basically give you threads. And a future is backed by a thread. A Scala parallel collection, each one of the items in the collection is backed by a thread. One future, one thread. One Scala parallel collection, one thread. So the future is a container, Scala parallel collection is a container. On the left here, the lighter blue, Akka has a similar stack to the Java stack, and you can see that the boxes seem to correspond. I admit that I jiggered the image around so it would seem that way. I took some artistic license, but in general, things line up pretty good. And the point of this whole slide is to say, if you have a future, you can choose to use a regular j.u.c thread, or you can reach over to Akka and say, give me a thread. And it'll work just fine either way. So depending on your use case, you can get your threads from wherever makes the most sense for you. And in a program, you can have multiple actor systems, as they're called, which are giving you the futures. And it's an unfortunate term, actor system, because you think all you're going to get from an actor system is an actor, but they also give you the actor futures. Anyway, if you need a thread, you can say, I like the configurability of the actor system, because I can specify a configuration file at runtime, and somebody who's tuning for a particular piece of hardware in a particular scenario can run some tests and decide what characteristics of that thread that they want, instead of using java.util.concurrent, where I'm hard coding the threads I'm using, the thread pools, the characteristics, and if you don't like it, you have to go and get that programmer involved again and test it all over again. And say, oh, we don't have the right test system, and so on and so on. So it's really nice to have this leftmost stack, which looks a lot. So basically what I'm saying is, you're used to using java.util.concurrent and how do threads work and all that. It's kind of the same with Akka. It ultimately ends up with the same thread, but the tuned thread that you get from Akka comes with a whole lot less pain and more reliability than the procedure you would have to go through. It's significant in terms of deployment, dollars and time and risk. You had your 5 options, remember? Java.util.concurrent, Scala parallel collections, Akka futures, Dataflow, and actors. So we're at Dataflow now. These only work with Scala. If you're a Scala programmer, you get to do this really cool thing. It's got peculiar operators. It kind of looks like your typewriter threw up on the page. I'm exaggerating. But you have some funny operators. And Each of those statements is written imperatively. It's easy to reason through your logic. This happens, this happens, this happens. But each of those happenings are in different threads. They're pulling data, and it's waiting until that thread's completed, and that's all hidden under the covers. So with Dataflow, you can write something that appears in an imperative style. Do this, do this, do this, do this, do this, and we're done. But actually, you're programming on many threads. Very unique, underappreciated. The documentation for Akka Dataflow is not all it should be yet. It's still pretty new. But Groovy language has a gparse library, and it was written by Jonas Bonner, the same guy who's leading the team in Akka. And so he did that there. And so if you look up gparse Dataflow, that's a mature implementation, a good job, and that's probably your single best source of what's Dataflow all about. And I admit that it has more in it now than Akka is showing. Perhaps that will change over time. So that's when I really wanted to understand what is an actor, what is a Dataflow. I went to gparse and I read there, gpars. So actors, I keep saying actors. Dataflow is good for coordinating things. So I'm going to take something from a future, something from an actor, and I'm going to do this complicated song and dance. These are, you can take a block, a Dataflow block, and then compose it, which is really cool. Okay, I'm talking about actors, which is the fifth, the most complicated option now, because I want to spend the rest of the time talking about futures. Actors can be accessed from Java and Scala. So if you're a Java programmer, you've got 95% of all of the actors' capability available to you. Do you remember EJB 2.0 back in, was it 92 or 93 or somewhere out there? And WebLogic was selling them like hotcakes at $40,000 a pop to everybody, whether they needed a servlet or not. All you needed was a servlet. I mean, you could have used JRun back then for free and it would have done the job fine. But no, computer fashion dictated that the length of the woman's skirt and the type of software you must use is pretty much the same mentality. I think that's happening again with actors. They've been around 40 years. They're not new. I admit the Akka actors are a significant improvement. They're very fast, very powerful, and there is a use case for them. But I want to say Akka does not equal actors. Akka is the name of a mountain in Sweden. Actors is a computing concept. Akka has offers you 5 concurrency options in total. This is one of them, and it's the one you should consider last, because this one requires you to reason about state in a distributed system. So the parts of your program, the problem you're trying to solve, that must be stateful across some sort of concurrency, maybe that does need to be an actor. But everything inside, you could have futures, you could use Dataflow. So just because you're using actors doesn't mean it's actors all the way. Use the right tool for the job. So actors, I think I mentioned before, can scale beyond one motherboard. Some very interesting things that you can do there. It also can be very difficult to prove that it's correct because it's not deterministic. And actors are influenced by the kind of a thread pool that's underneath. So something I see that people make a mistake a lot is, I started off this talk by talking about thread pools and characteristics of thread pools. You should understand that if we go charging off and say, I'm going to use actors or I'm going to use features, because if you don't have any understanding, stick with fork join or cached or fixed or whatever, and hope that you don't hit one of the many scenarios where my program doesn't work. I don't understand why, and it seems right. Well, it's right, except to pick the wrong thread pool. So it does require some investigation. Okay, so now I reached the main part of the talk, which is Akka Futures. Again, if you're a Java programmer, you can use them. And of course, it works from Scala. Now, the verbosity of Java compared to Scala is, I don't know, 5 to 1, some people say. In this scenario, when it comes to futures, because there's a lot of closures involved, which are anonymous classes, it's more like 10 to 1 or 15 to 1. So a 4-line Scala program might be 2 pages of Java, which can be difficult to read. Now you can mix and match. I mean, you can write part of it in Scala and part of it in Java. That's fine. It works great. And I encourage that. It's not You have to do all. So what might be interesting to you is if you need to do some parallelized stuff, and you want to use futures, and you want to use composition, and you just want to be able to understand it easily, why don't you write that part in Scala and then call it from Java if you're a Java shop. So you've got 20 lines of Scala you have to support, and all the rest of your program doesn't change. You can get a lot of mileage that way. A lot of people are doing that. Futures are easy to reason about. You can understand what your program is doing. It's deterministic. And if you follow the guidelines, it should be repeatable. So you can run tests on them. You can have confidence that it actually is doing the right thing. So one of the rules that you have to follow is that the payload, the callable, should not have side effects. It should be idempotent, ideally. You should not be accessing global state. I'll allow you to do a println for debugging if you want to understand what's going on, and I'm going to show you that. But if you have a future and you say, okay, now I'm going to write the result back from the future to a piece of main memory, you know what happens, right? Cache line, ping-pong. Don't do that. There's a way to get the answer out of the future and then put it all together. So one more time, what is a future? It's a holder for a result that will become available at a future time. Every future has a thread that it's backed by. Now, if a future, this holder, has actually got a left and a right. If you have a good result, the value will be stored on the right. If you have a problem, the throwable will be stored on the left. Futures have 3 states. Pending, no answer yet, we're not done. Or we have an answer and it's failure. Or we have an answer and it's success. Pending, success, and failure. Twitter's futures and Akka's futures share a lot in common. I'm not going to say much about Twitter futures. I could talk to you about them, but we probably don't have much time. But here's what I can say, that together they share these characteristics. They are for managing concurrency. They're both higher level, much higher level concept than java.util.concurrent. They are immutable. Once a value is set, either on the left or on the right, you can't change it. So that's so that you can have functional programming. So if your future resulted in an exception or a throwable, that you can't come around later and run it again and change that value. You have to make a new future, run the same computation, and get a new result. And that's how you get thread safety. Yes, it uses more memory, but that's cheap. Don't let that hold you back. Futures are cheap. Threads are expensive, but they're coming out of a thread pool. We can reuse them over and over. Futures are cheap. So if you need another future, make it. You can preset a future to a value. So if you're writing tests or you want to play some games, I'll show you in the demo part, and I'll do that a bit. And you can also preset it to a throwable or an exception. And when you start a future in motion, you can wait, you can block for a result if you so choose. Generally, it's not what you want to do. You're writing futures because you want to have asynchronous programming that doesn't block. But every once in a while, you need to collect all the pieces together and say, the answer is 42. And in order to do that, you're going to have to block somewhere. But there could be many futures that are not blocking. So composable futures, this composition thing. Remember that you have an operation which will be initiated on a thread that will run to completion. At a future time, the result will become available, and then you can take that result and do something else with it, perhaps another future, which takes some time and ends, so you can compose these things together. I want to, in my program, do computation number 1, followed by computation number 2, computation number 3. They all take a period of time, and so I'm just going to write it, do this, do this, do this, future, future, future. Pipe the results from one to the other, give me the answer. That's composition of futures. And so that whole thing runs by itself. You don't have to wait and block for that. So we have transformations on a single future, and we have operations that we can do on collections of futures. So remember the map reduce thing where you had a piece of data and many threads running on it, and they're all crunching away, and finally you collect all the results back. So the reduce part is working on a collection of futures. You can manipulate collections of futures. Here's all the operations that you're likely to need. that Akka supports on futures. And this is as of Akka 2.0.1, which is current today. It always seems that next week there's another operation, but at this moment in time, these are the ones that you probably want to consider. So you have the workhorses, flatMap and map, and the demo will talk about that, so it might seem a bit weird to talk about it in the abstract, but it makes sense in the practical, so I'll just defer that. Fold, that's a kind of a, the map reduce thing. That's where you collect your answers together. You can sum up all the numbers or concatenate all the strings. Fold is good for gathering a bunch of results together. For each, again, if you have some kind of a collection, you can iterate. That's your iterator. Zip isn't as popular as you got two answers and you combine them with. Flow is where you take a future and you pipe it into a Dataflow. So that's how you connect Dataflow with future. So if you're playing with Dataflow, you'd want to know about that. Then you have these collection operators, reduce and sequence and traverse. They're kind of related to fold, actually. I should have put them all together. These are just ways of taking collections of futures and coming up with some kind of result from that. And then you have error handling and sequencing, and they're somewhat related. So try, catch, finally constructs would be built out of things like on complete, on failure, on success, recover, and fallback to, and then. So all that stuff at the bottom, that's try, catch, finally. I have a code example for that. So who's using this stuff? Twitter uses Composable Futures exclusively to do all their tweet processing, many tens of thousands per second, done with Composable Futures. There's a huge amount of horsepower, heavy lifting being done with Composable Futures. Clout, it just a few days ago released their their new API, and it's based on Composable Futures as well. I don't know what they were using before, but they say that their server load dropped in half when they started using this. Just a slight digression here. We'll come back to the main theme, but I wanted to say that when you have a concurrent or a parallel system, it's by nature, it's statistical. It's not entirely deterministic. In other words, each time you run it, things will take a little bit longer. The sequences won't necessarily line up exactly the same. And so if you're doing benchmarks, you're going to get a different answer each time. How long did it take? So I've written this little benchmark program which will be published in InfoQ next week. And it can work with two kinds of containers, Scala parallel collections and Akka futures. And it shows you the red bar, which is the minimum expected time to do a task, the task that you've given it, and then the blue stuff, which is 2 standard deviations beyond that. So blue says, this is your expected variance, and here's the minimum. So you can take that benchmark and run it on a variety of different thread pools, and you get many different results. Yes?
Last two bars are labeled the same, right? But the expectation is very different. Can you explain that?
Oh yeah, when I did this, I had a very long label. The important thing was 1 thread for the second last, 8 threads for the very last. 1 thread for the second last, 8 threads for the, and then 1 thread. So more threads, shorter time. In the version that's been published, I should have updated this slide. I have much shorter labels, but they're so short you need a legend to see what was this. Here I attempted to write a story on the y-axis as to what it was, and it clearly didn't work out. The moral of the story is different thread pools with different characteristics will affect your program in a major way. And there's some variance. So blue shows you the range of expected values. Let me show you that in more detail. Statistics, who knows what a standard deviation is? A lot of you. So I don't have to beat this to death. Okay, so basically there's a mean. It's kind of like the middle point, sort of the expected value, almost like the average. And one standard deviation either side is we would normally expect that the values would be within less than or greater than one standard deviation. So if you have a tight clustering of values, this is a highly repeatable test. It gives you almost the same answer every time. Then you have the image on the bottom where you have a very small standard deviation. But if each time you run the test you get really different numbers, you have a big standard deviation, more like the image on the top. And so here we have the blue section at the end, which shows you expected variance. I've superimposed this little Gaussian distribution, and you can see that there's actually 2 standard deviations. That's all that this test is doing for you. So the point that I wanted to make was the kind of processor you have, the number of CPUs, and other things about your hardware will affect how a concurrent program behaves. And so if you test it again on a very different kind of a computer, you're going to get very different answers. It might test well on one system and poorly on another. Thread pools can also affect each other, because if you have a CPU, let's say you have a CPU-bound task, it's maxing all your cores, you're drawing a lot of power, it's computing pi to 1 billion decimal places on all your cores. So the fan on your machine is screaming, you're drawing a lot of electricity, and there's no wait. All your threads are fully occupied. If, on the other hand, you have a web crawler and you're fetching lots of web pages, you're I/O bound, and most of the time your CPUs aren't doing anything. So they're very lightly loaded. And so what you can do in that case is you can allocate many threads per CPU, because if 90% of the time your CPU is waiting for some information to come back for the web, why not just allocate 10 threads per CPU so your CPUs are busy? And so knowing how to balance that can only be found empirically. You can do an initial estimate, but you're probably wrong. It's better to measure it. Better to measure it on the system. And that's, as I mentioned before, something great about Akka, that you can, you've got these config files. You don't change your program, you just tweak the config file, run the test, or run your program, say, this gives me the best performance, that's what I'll use. Demo time. Any other questions before I hit demo time? We all love demo time. Okay, so we'll start off easy, and we'll get more complicated. I have here for you IntelliJ 11. I don't need to use any IDE for this. I could be using a console, but what this does for me is it allows me to cut and paste from the top to the bottom, so I don't have to worry about being a good typist. And believe me, that's important. I'm going to show you my build file. This is all Scala. The reason I'm showing you Scala is because I have a REPL, read, execute, print loop. It's an interpreter. I can type in code, it gets compiled right away and run, and it remembers everything it did. I can't do that in Java, and so it's harder to demo Java. But I can show you equivalent code if you want, because I've got this. All this code comes from the book. I should point out that, for example, in the Java section, these are the programs. Each of these is a separate program of different things, different concepts. And you see the same programs again, but written in Scala. So all of the code you're seeing has been called from that. So in the build file, which the build tool is SBT, it has been, people have a love-hate relationship. It can emit an Eclipse file, and it can emit an IntelliJ IDEA file. I'm using IntelliJ, so that's fine. I'm not going to take you through the concepts, all the stuff in here, but all I want to say is at the bottom, where I mentioned after all the dependencies, every time I start my REPL, the read, execute, print, loop, the interpreter thing, all this stuff gets executed. So it's nice that I don't have to say, re-import these variables into the interpretive session each time. It's done for me. I don't have to redefine all the variables I want to mess with. I don't have to. It also loads all of the compiled assets from this project. They're all available to me too. So I have my program sitting in front of me and I can call any piece of it. It's very nice. So we're going to do that. So I've already started the REPL, and you can see that it's already imported all these things and defined some variables. So I'll go back to my demo one, simple futures. Okay, so it's defined a random variable, and you know it's like it's the same random you know in Java, really, basically. We're very similar, and I can run that, and it picks value. And reading the response, can you all see that? Oops, don't look at this. There, can you all see that thing at the bottom? Who can't see the bottom of the screen? You're in the front. You should move forward. Everybody else behind you apparently can see. Sorry. So I typed in random.nextInt, and it answered back res0, which is the name of a variable it created, :int. So this new res0 variable is of type int, and it has a value, a big number. And I can do that again. We should get a different number, right? And we do. I can also do some higher math. 1 plus 2. I got 3. Look at that. And it's of type int. And it's stored in a variable called res2. Okay, so you can type in any expression. You can evaluate anything. Whoop-de-doo. All right, so we have, come back. Expensive calc. Now, all this does is square two numbers. It's not that expensive, but I just imagine that it was an expensive calculation because we're going to do stuff like that. It gives you back an answer. It just multiplied that. I'm going to make a future. I'm going to call it F, and this future will be composed, it will be created by adding 1 and 2, and we're going to get the answer back in the variable F. And so let's see what we've got at the bottom. It says F colon, so we created a variable called F. Its type is an Akka dispatch future of type int. So the value is an integer. So it's a future holding an integer. And equals, and then it's Akka dispatch default promise. So what you end up learning here is that futures are actually built out of promises, and there's a specialization of a promise called a default promise, and it doesn't matter, move along, nothing to see here. If you're doing system integration work, you care about promises, but on Futures 101 day, we just skip lightly by. So I wonder if this future is finished or not. I hope it is. So I'll just find out. I mean, F dot is completed. Except I can't spell. Oh, good. We got a variable, res4, of type Boolean, and its value is true. So yes, the future is completed. All right, well, let's see if we can get the value. And this is where you'll see something, value. Well, first of all, we have an option holding an either, which can have two things in it, a throwable and an int. Huh? Well, remember I said futures have three states, pending, failed, and success. So on the right-hand side of the equals, it says sum right 3. So we got some value. So it's not pending, it's complete. The fact that it's complete, we know that because it's of type sum. Inside the sum is a right. So we know that there's nothing on the left, because you can only have something on the left or the right. Stuff on the right is your success value. Stuff on the left is the exception or the throwable that you had. So in this case, we can say, we got a value, and it's an actual, this thing's completed, the future completed, and the actual answer is 3. Well, that's pretty awkward. How do we get that stuff out anyway? Well, okay. I'm going to save myself some typing here. This is at a funny angle. It's very difficult to type. So I'll just show you a piece at a time. F.value.get strips out the option part. So now we have a right of 3. And then if I just say F value get right, we've got this right projection thing. If you just want the value, never mind. I know it's a good value. Give it to me. That's the incantation. But you wouldn't write this. Well, you're more likely to write it if you're a Java programmer. But if you're a Scala programmer, you've got another option available. If you're willing to block for the answer, is a very convenient way of getting that answer. You can say, I'm willing to, in this case, I'm willing to wait forever for f to complete, and when you get the answer, show it to me. And there it is. Okay. There's a variation where you can ask for 1 second, and notice that we have a domain-specific language here kind of thing. You actually write 1 second, not 1000 L or whatever. It's kind of nice. So you might ask yourself, okay, if I create a future, when does it actually start working? So what do you think? If I type in this evaluation, will the future start executing as soon as it's is defined, or will it wait till I do something? Who says it's going to start right away? Who says that you've got to wait to kick off the future? Okay. Yeah, I wondered that too when I first started. Well, let's find out, because we'll find out right now. I defined the future, and immediately the print showed up. So you know that the future started executing immediately. It actually happens as soon as there's a stack frame available for it. I didn't say thread. So the reason I said that is because every executing frame has an active stack frame. But if you are node.js, you have only one thread, and everything happens on it. And so things get shuffled in and out with lots of stack frames. Crazy, I know. So it's possible to have an Akka program run on one thread, or not all Akka programs, but many of them, and certainly this one. And so that's why I said stack frame and not thread, because it will always be a separate stack frame, but everything, we don't know, we shouldn't be making assumptions about the threads that are supporting a program unless there's a particular reason to be able to do that. So if you're a Scala programmer, you might write this to obtain the result. So I'll just explain this. If the future f, or when the future f completes, then there's two cases to consider. One is we have a result on the right, and that's just a good result. In this case, we're just going to print it. The other case to consider is we have an exception or throwable on the left, in which case we get the message and print that. So that's a way of getting the answer. So let's try that. The answer is 3. Very nice. So this is asynchronous programming. Inside the squiggly brackets, you've got some code which gets compiled into a closure. And so all of this stuff makes an anonymous function which gets executed. And so that's a callback. So it's possible inside this function to attempt to change the value of the future, and it will fail, because futures are write once. And so although you might think that you are putting in another value, if you returned 6 or something, you're not actually changing the value of the future, and that's a common cause of mistakes. So if you, I'll show you some other try-catch finally. I just
you define if you are the future and you again define
yeah. How's that possible?
How is this possible?
In the REPL, rules are a little different. You can redefine it. It's an interpreter. It's not the compiler. Some things are a little different in the class loading is quite different. The thread management actually is a little different.
The second question is that you notice that when you're starting something new, you are at the bottom, the number of processes start increasing. If you're available 9, now it's 7, then what's going on behind there?
In the REPL, every time you hit enter, you start a separate thread. So the REPL, of course, is not a production piece of code. It's something to help you figure out what's going on before you write some code. And so it's somewhat wasteful of resources, and it allows you to redefine things. It's more of a guide to what to expect from your program. It isn't 100% fidelity. Thanks for coming up to the mic. Okay, so let's try simulate an IO-bound program. So what we'll do is we'll wait for a second and then print 1 plus 2. Store that into G. So actually that's 10 seconds, isn't it? 10,000. And we have an answer. Oh, I was supposed to do this quickly. I'll do this again. I'll do them together. So watch. Pretend I can type really fast. I threw an exception because I said await for 0 seconds for a thread that will take 10 seconds. And that timed out. And it threw an error saying you timed out. So you can do that if you're blocking for an answer for a period of time. It's an option you have. However, if you use the callback format, there is no timeout because you're not blocking. Okay, let's throw a different exception. Let's divide by 0. So first of all, this really complicated program is going to create a future which divides by 0, and we're going to, this exception is now stored on the left. There is no answer there's no value on the right. This future failed. And so we can get the exception. If you're a Java programmer, you might do it this way. And you see arithmetic exception, divide by 0. And if we do the same thing as we did before, this is the same code I had typed in before. The right clause is not going to be triggered. The left clause will be triggered. It will match. And so it just shows me the error, which is arithmetic exception, divide by 0. Okay, so let's do something more interesting. Here's a little one-liner, which counts all the lines in a program. I'm a 24-point type. It's hard to read. There you can see that. In Java, you'd write a bunch of lines, but this is Scala, and so we can use slurp string to go out and go to a URL, read at the contents, use UTF-8 encoding, and return the result. Okay, so we've defined that method. Now we're going to a place that doesn't exist. We're going to get an exception. We're going to go to the website booboo, and there's no domain name. This will fail after a timeout. And now I'm going to do this a little bit faster because I'll just do it all at once. And so we didn't actually, this await result, it failed. But you could also do the same thing by going to a valid website, the Akka website. And now what happens is it goes to that website and it pulls everything down, the contents, and then it splits it all into separate lines, counts the number of lines, and that's the answer that's given back. And that's stored in n lines too. So there's 439 lines in that program. So it was really nice that we were able to write a future. Imagine you're writing a web crawler. You're spinning a lot of threads. You want to get some answers back. Your web crawler written in Scala with the futures is going to be a really small code, a small program. To do the same thing without futures in Java, be a really big program. And so this last, I think I'm beating it. This is just beating a dead horse here. Let's move on to our second example. Try catch finally. So there's many ways of doing try catch finally with Akka futures, and it's a very flexible construct. First of all, I've broken this into pieces. I want to have a computation that computes a value, and if that value is even, gives me true, and if it's odd, give me false. Unfortunately, I've set this up that we're going to have a divide by 0 error instead. So let's just watch that happen. Boom. It blows up. Okay, so I guess we need a catch clause then. If we're going to throw an error, let's make sure we can handle that. And the computation that you see is the same computation we had earlier. So it's a big long thing. You know, HTTP get, we're going to split, we're going to get the size, but that's what you saw earlier. We're going to do that again, and we're going to tack on at the bottom this recover clause. So this extra recover clause says if there was an error, if we had a throwable, then depending on the kind of error it is, if it's an arithmetic expression let me know. Just print it out. That's for you. You wouldn't have to normally do that. And then pick the largest possible integer. And otherwise, with some other error, give me 0. And then this will create a new future with those values in it. So if you had a good value coming from the future, that future is preserved. If, on the other hand, something on the left threw up because you had a throwable, then we'll create a new future, and we're going to pass that along to our variable instead. And then at the bottom I say await. So after we're done, just show me what we got. So because I don't want to try to type this, I'll just paste it all in and see what happens. So we threw the error, and then we recovered and said we got an integer result. That's the largest possible integer. So that actually did what it was supposed to. The original future divided by 0. We caught that. We said, oh, it was a divide by 0 error. Let's return the largest possible integer. That got wrapped into a new future. And then we said at the bottom, let's wait for that answer and then print it out. Okay, so we got try and catch. How about finally? Well, we wanted to know if it's even or odd. So whatever the number is, we're just going to see is it even or odd. If we're going to return true or false, right? And so in this case, we can use map. So one characteristic that map has, we're starting with a feature of type int. It tells us how many lines we had. But what we want is true or false. So we want to change the nature of this feature from int to Boolean. Map can do that. Map can take one kind of one class and produce another class. Lots of these, in fact, all the other transformations can't do that. Map is unique in this way. I guess flatMap too. So let's try it. Map is very useful for that reason. So what we should get is a Boolean, true or false, and it's false. So I guess it's an odd number. And let's take a look at it, because you didn't get a good chance. See, if on the map here it says, if it's an integer, then I want you to divide it, well, percent 2, take the modulo of 2. If that's a 0, it's an even number. So it's true. Otherwise, it must be false. It must be odd. That's all. So, oh no, I gave you the logic is wrong. If this evaluates true or false, that's the answer. If we had something else other than integer, I'm returning false. If somehow we had a real number or craziness that crept in, I didn't want it to just fall through. It's good to have some defensive programming. You might want to ring an alarm or whatever. In this case, I just gave it false. If it's not a number, it's not even, so it must be false. The slide actually, I think, makes it much simpler than the code I'm going to show you. So flatMap can be used in two ways. One way to look at a flatMap is it's a combination of map, which you saw you can turn a something into a something. You can transform from one type to another. And it also can do flattening of a list. So if I had a list of collections, flatMap could come along and collapse each collection. So I could just have a list. So if you're not a Scala programmer, then option doesn't mean anything to you. But the thing I wanted to show about flatMap wasn't that property. It was that if you have something you want to do, and based on the result of that, you might do something else, then flatMap can be used to do kind of like an implicit if-then short circuit. So if this, then that, and then maybe this, and then maybe this, and maybe this. And you can write a lot of code that's deeply nested, or you could use flatMap, and it just skips all the inside, and that's what I'm going to show you now. Now, this demo is based on Marius Eriksson. He gave a presentation to the Bay Area Scala enthusiasts last week, and this is based on the Twitter authentication. So it's not abstract. It has a basis on how you log into Twitter. But he did it with Twitter futures in kind of pseudocode, and this is real active future code because it runs. So basically what it does is it's a two-step process. Given a token, look at find a user ID. If there's no user ID, fail. If you haven't failed, take the user ID and find out information about the user. Get the user object. That's all we're doing. Here's a summary of the code. So user f here is a variable. Actually, it's a write once variable. You can only set it one time. It's of type future, and the future will have it will contain a user object. And that's if it doesn't fail. I'm taking a shortcut here because really you'd have an option, but anyway. So what we say here is we're going to authenticate the token on a thread. So because this is a long running process, we're going to run the authentication process on a thread. That's why we're wrapping it in a future. And when that future comes back, we either got something, we got a value, or we threw an exception. No such user. So if we got something, we're going to call flatMap, and we're going to pass in the user ID, and we're going to get the user object. And if we got an exception, we're not going to do any of that. We're just skip it. And then after all of that, we can conditionally do something with user f. So the onComplete clause, this is a callback. If we had a value, print it out. Otherwise, print the exception. So that's kind of like a pseudocode. So let's go to our demo. I've broken it into little pieces. There's no database for this. It's just a hard-coded match. So authenticate, here's our authentication program. We pass in a string. If the string is the magic string, ASDF, you're authenticated. And your user token is 1, 2, 3, 4, 5, 6. Otherwise, we fail. And I use promise here. Because if I want to say I failed, it's easy to do it this way. I call promise, say I failed, here's my exception. Now promise is a future, so this is the Akka way of saying, look, if I ever get here, this is a failure. I want to show you this way. So hopefully that's more helpful. So, and then I'll call this authenticate. I'll just define it here. And now we'll call it with ASDF. It should wait up to 1 second. It'll be faster than that. And we got a long, and it's 1, 2, 3, 4, 5, 6. Big deal. Let's try failing. So we're going to try authenticate some other string, and boom, and printed the exception. Okay, that's very nice. Let's try this now, the second part, the get user part. So we're going to start from the ID, the long that we got, and if it matches the magic string 1, 2, 3, 4, 5, 6, we will look up the user object, and lo and behold, it'll turn out to be Fred Flintstone. If, on the other hand, it was some other ID, we are going to fail. So let's define that and pass it in all together. And we have a promise. So let's just see what we got. Oops. It's hard to work on this setup. There's Fred. Okay, so we did authenticate. And similarly, if it's something else, it blows up, just like you've seen before. So let's put it all together. The flatMap is in here. So we're going to look up a user. We're passing in a token. We say authenticate this token. We get a value or it blows up. If it didn't blow up, then flatMap is going to do something. If it did blow up, flatMap gets skipped. And so the authentication will give us a feature which will either contain an exception or a value. If there's an exception, that feature will be passed back intact. If there was a value, then that feature gets unwrapped by flatMap and passed. That's the thing. It gets unwrapped by flatMap, and the value gets passed into get user. So that's what flatMap is doing. It's unwrapping the future. It's getting the value out. You can think of future as a container that way. And so I've defined that, and let's try looking it up. And Fred is there. So that's kind of what I have for you. Any questions? Well, in that case, I believe I'm done here, folks. Thank you very much.